I would like to start by giving you some concrete examples of the power of controls. I work a lot on control systems that look like this. I worked a lot on how a semiconductor industry manufactures the computer chips that is used in computers, cell phones, tablets, etc. It's a control problem you see over here. We are controlling the motion of these wafer stages down here precisely to make the process called photolithography happen in the way that we want. And then I work a lot also on nanometer scale precision control in something that you find in everyday life. It's perhaps the best example about precision control that we can find in everyday life. Just $70 and you can have a nanometer precision control device. The read-write head in these hard disk drive systems, they are doing super fast and very high precision control, okay, of the motion to either read data or write data onto the spinning disks. I also work on robotic systems that look like this, mostly for manufacturing, and it's very playful. I find it super fun to work on these problems. We can solve a Rubik's Cube using robots, but this is just a demo. It turns out many of the techniques we do here can be translated to do vision-based inspection for example, aerospace industry. Another example that I do myself is in manufacturing systems about using laser to process materials, very fine materials of powders, either metallic or polymers. This is super useful nowadays to make parts in complex geometries and shapes for use, for example, in engine for aircrafts. Or for aircraft, there are special components that we want to use less materials, then we can have better fuel consumption, and then we can fly longer using lighter aircraft. And then there are a lot of scientific discoveries about being able to make things complex and in a very rapid fashion. So there are lots of papers, a totally very exciting branch of papers about metamaterials, for example, that they use additive manufacturing. To give you guys a little bit more specific ideas, for example, this is the control that we talked about photolithography, where we use projected lights to build billions of transistors onto the chips that are the size of a fingernail. So this is repeated down many, many times, and then it's done in a very clever fashion because if you think about it, the features that we want, that we build into computer chips, they're so tiny. How can we make sure building such features precisely? It turns out we have big patterns originally. We have a mask, and then we project lights onto the mask, and then we use lens to focus this pattern onto these wafers. So we need to control the motion of this wafer stage and the reticle stage very accurately. And if you imagine how it looks like in reality, drive from the airport to campus, drive it once, drive it twice, and then the resolution of the control here is the tires, the trajectory of the tires must be maintained, millimeter scale error tolerance. Human cannot do this. You must use advanced control techniques. And you have to maintain the same tolerance every day, okay? So with weak control, we cannot do that. With enhanced control, we can reach such kind of resolution. More broadly, control is super important. We have lots of faculties in the mechanical engineering department working on precision control problems. Okay? I'm doing some of the things that you see here. Just recap about the control problem here. It's like flying at super high speed, an aircraft, but above the ground, just a tiny little bit of space above the ground. And you have to switch lanes very rapidly, like this. And then you need to maintain the tracking of each lane accurately. Nanometer or micrometer scale precision control is a very important area that utilizes control heavily. I'll talk a little bit about some of the things we do here. My hope is that by introducing these examples, you will see how a control problem is formulated and then solved. When we work on precision control of a very high speed spinning disk over here, and then we need to access data very frequently, then there are these problems about vibrations. And these vibrations are because when we cover the disks is an enclosed space, and then we have high speed airflow inside the space. This read-write head is literally just a tiny little bit of space above these spinning disks. So the complex aerodynamics creates vibrations. What we think is a super flat surface is no longer a super flat surface at nanometer scale precision. These vibrations, they look like this. Many of you learned fast Fourier transform already. So that's how we utilize those tools in analyzing problems that look like this. These vibrations, as long as we know how the nature of it, we can create controls to reduce these vibrations from here to here. All right. The disk drive industry is now moving more forward to enterprise storage, where we use them in clouds, in data centers that look like this. This creates new problems. What was working perfectly fine may not work as we desire in this new application, because whenever you stack a lot of precision mechanical components together, you face the challenge of vibrations propagating from one disk to another. So it's a super important issue, actually, because bad things can happen if the control is not done well. So this is true story. Just happened in 2016. Okay? So the vibration from the construction, actually from the sound from the construction, is not enough. These drives of a bank data center. Controls are getting new problems over here, because if you imagine how our acoustics work.
Excuse me, Professor?
Yeah.
Can you pause for a moment?
Okay.
Do you have a cell phone in your pocket?
I do.
Can you put it away?
Does it work better? Better?
Yes.
Okay.
Thank you.
See, right? Acoustics, vibrations, real problem. This is super complicated problems, and it's new to control because you all guys know about the concept of bandwidth, which is below the bandwidth we can do well. A classical control can do well. But these vibrations from the acoustics, from the sound, many of them are high frequency. Okay? When we speak, human voice can go kilohertz. These vibrations are not covered by conventional controller, and then they are not single frequency that we saw previously. It's much more complicated. It's a very wide frequency band and the multiple bands. This is also depends on the environment, obviously. So control is even challenging here. And with good controls, we can reduce these vibrations from these at multiple frequencies. All right. I have tons of other examples, and then maybe today I will stop at one that I hope will be really intuitive and interesting as well. If you think about how humans do control, it's not a precision machine, it's not a disk drive that I can do nanometer scale precision control, but human can do things like this. This can happen in reality. Human can do, when we play tennis, human can go from this to something like this. We can catch a ball that's very high speed during normal. I cannot compete with them. You probably, many of you can't, but some of you may become future tennis players, can compete at this level. But you see the point. Control is something that we can learn. As we understand the game better, as we understand our opponent better, then we can build models, we can train ourselves, and then if we do hard enough, we can do things that wasn't achievable previously, and we can get super excited about it. What we do from that point, if you imagine the key problems over there, one of the components is that humans use vision a lot for playing tennis at least, right? Maybe we use our ears as well. These are sensors that have fundamental limitations. I cannot see from here to the East Coast, right? I cannot hear what's happening in a different town. These sensors, they have fundamental limitations. Cameras, they have usually 30 frames per second, 60 frames per second. They have limitations on how fast it can measure. But human, you see the example on the previous slide, human can learn from that. Human can do things using these slow sensors. They can play tennis at a very higher level. We're doing something using slow vision sensors, and then in view of also the potential delays in this communication with this large video data. It turns out by doing controls by doing modeling in a way tailored for the application, by doing control of the sensor, we can create algorithms that look like this to be able to track a moving object from with standard control. This is also with control, but with standard control. And with some advanced control, we can do better at least. These are some examples, at least I do, in my research. There are a lot more, as I mentioned. The field of control, I think, is really exciting. And as we together move on in this quarter, I hope to introduce more examples to you, either from my research or from colleagues at the ME department or somewhere else. Thank you. Yeah. All right, that's the outline. Power controls, concept of feedback, and then terminologies. We demonstrated nanometer precision control, laser-based additive manufacturing, and then robotics for manufacturing. I didn't talk about this one yet. I might come back to it someday in the future. These systems, the control language that is used to work out the planning of these systems, most of them are based on linear control theory, which is what we talk about in this class. The scope of this class is about analysis and control of linear systems, linear dynamic systems, to be more precise. In this set of notes, I would like to formalize these concepts clearly to you guys, starting with systems. So a system is an interconnection of components that serve some purpose. Human is a system. It's the integration of body, different components. Okay? It's a very versatile system. In a hard disk drive system, it's formulated to do one thing, and to do one thing really well, which is controlling the read-write head to access data. So a system can be uncontrolled or controlled. The control system is the integration of these components, forming a configuration, okay, a system configuration that will provide the desired response. So there is this response, concept of response in a control system. We would like to apply controls, and then we would like to see response. And then we can use that response in what we call feedback. Feedback is the use of information either from the past or from the present to influence the behavior of a system. In all these examples that I talked about today, they use feedback. It happens also in everyday life if you think about it more, and you can come up with a lot of examples, I believe. So every day I wake up, when I wash my face, I do feedback control. Why? Because it's winter time here, and the water is pretty cold in the morning. How I adjust the temperature of the water is a feedback control system. I first turn on the cold water, and then I turn on the hot water. It's not like an automatic process, right? So I need to adjust how much hot water that I will get to be able to get the temperature that I want. So it's a feedback system. It's a control system. Now, that's just one example. But if you think about it, why do we need automatic control? sometimes it's for comfort. If I have warm water, I feel more comfortable. But also, there are many applications, feedback control, automatic control is super important because the technique, the things that we do, just human cannot go, right? I cannot put my arm in the oven to measure the temperature. We have to use the feedback control system, right? So stability safety is a big issue. Some tests may be difficult or impossible for human to do, right? So we need computers to do that. Or it may be just the performance. I cannot do nanometer scale precision control. We need these advanced control techniques because humans cannot do as well for many tasks. And then also, humans can get bored, can get tired in many applications, right? So cost, either time or money, is another issue for the importance of automatic control. Now, those concepts is relatively intuitive. Now, I would like to talk more about the language we speak in control system analysis. Most of the things we do in this class can be translated into a block diagram that you see here, where we have a process, which is the thing that we want to control. We want to control the output of a process, right? So it's either the temperature of the water that I use to wash my face in the morning, or it may be the position of a read-write head in disk drive systems. So there is the process that I want to control the output, and then I have some actuation to be able to influence. So the actuator is a device to influence the controlled variable of the process. The actuator in my washing my face example is the knob of the faucet, right? So if I drive a car, the actuator would be my pedal that I can control the torque of my engine. So the actuator and the process together, they form a plant, okay? The plant is what we want to control using a controller. So we generate some control command to this plant through the actuator and to the process. So there may be additional components, obviously, right? So we need sensors to measure what's going on. We need sometimes to filter a little bit of what I want in terms of feeding back to the system, right? I may want, I have a concept of temperature that I want. I may need to translate it a little bit so that temperature, the HVAC system in the house will look like. So I have a desired, this is what I do nowadays in those thermostats, right? You can program it, I say 6 degrees when I'm out, 69 when I'm back. We need to filter what we want. We need to do a little bit planning before we send this information to the controller. So input filter, this is very common in many control applications. All right? Very importantly, there's nothing that's perfect in practice. A lot of process or plants, they are imperfect in many ways. So there will be disturbance going into the system. For example, if I drive a car, it's not just me driving, like everyone is on the highway in the morning. The disturbance is all those congestions on the highway. And then the sensor is not perfect either, right? So I talked about vision has limitations on the speed that I can measure. In a lot of sensors, there are other kind of noises as well. All right. Reference is what I want. It's what I want the system output to behave. You guys probably are very familiar with the concept of the difference between open loop and closed loop control. So open loop is something that looks like this in a block diagram. You have what you want. You have a system to control, and you just go forward. It's like if I want to walk a straight line, I close my eyes and then walk. That's open loop control, right? So I don't do feedback in open loop control. I don't measure the output of the system and use it to improve my control. That's the main concept of open loop control. Very importantly, the control system that we deal with, this desired output and this actual output, they are signals. They are usually not like a constant value. So they are functions of time. So either is the speed of the car or temperature in the room. They are all functions of time. These are signals either as a continuous function of time. For example, if I want my temperature to look like some profile that looks like this, maybe. It's cold during the day and it's warmer when I come back. A signal can also be discrete time signals, meaning that a signal can be something that looks like this. It's still a function of time, but it's updated only at specific time instances. So as a matter of fact, modern controls, the direct output from the controller is a discrete time signal. It's updated at every sampling time of a computer CPU clock, for example. Right? So signals can be both discrete time and continuous time. My notation is usually discrete time and then continuous time, dt and ct. That's open loop control. Now, closed loop control is what we do a lot, what we need to do a lot, actually, in practice. Because we talked about there are disturbances into the system, and then there are sensor noise, and then plant is not perfect as well. So what we do is we use feedback. Use feedback to be able to accommodate some of the disturbances over here, some of the sensor noise over here. This is a closed loop system, okay, because these components have a closed interconnection. So we have a loop over here that is closed. So a closed loop system always has feedback. And the purpose can be, there are many ways that we need to do closed loop. Disturbance accommodation is one of it. And that's one important aspect of it. All right. Let's work out an example about temperature control. It's an HVAC system. Let's think about the concepts of plant, actuator, disturbance, controller, how they can put into this block diagram. Here, what I want to control is the temperature of the room. I have some desired value in my mind. Okay, so I set it in a thermostat. And then the thermostat is going to do, nowadays, usually PID control to the house. What is the process that I want to control? Is perhaps the whole thing, right? I want to be able to control the furnace, how it generates heat to heat up my house. The process is actually involves its own complicated dynamics, if you think about it, right? So to heat up a room, there's convection, conduction, all these physical process happening, right? So these are what I want to control. It is a process, okay, that we formulate and put into a block diagram. What is the actuator over here is the valve of the gas that goes into the furnace, right? That's the actuation that the thermostat can control. So the thermostat will send out either current or voltage signals that will define how the degree of open for the valve, and then that valve is going to influence the process. And then we have the feedback. The controls is being done over here. So obviously there is heat loss in winter, right? A lot of the heat will be lost in the process. It's either the furnace is not perfect or the house is, the temperature outside is low. So this is the disturbance. Right? That's how we can treat the system in a block diagram terminology. So now let's look at another example as an exercise. Think about the control system in ACC, Automobile Cruise Control, which is very popular nowadays. We have engine of the system. We have an auto body. We have sensors that can measure how fast the car is moving. And then we have a controller. It is a human or an autopilot in some of the modern cars. The control objective is I want to be able to, so in ACC, in cruise control, the control objective is to be able to follow a constant speed that I set, or if there are cars in front of me that blocks me from going to that speed, I will try to follow that car. I will try to follow the speed of that car. That's the objective. Now, with that in mind, what is the process? Output, actuator, sensor, reference, and disturbance. So I will give you guys a little bit of time to think about it, and then we're going to work it out together. All right. Any volunteers want to talk about it? What's the process? Let's start with the first one, maybe. Process is a moving car, right? I have an engine that generates torque that translates to the wheels, and then the wheel will move my car. This is the process. That I want to control, and the output is the speed of the car. The actuator is the pedal that I can control. A human is the controller, right? So this is the actuator. So the whole thing together is the plant. Usually in this class, we say we use P to represent a plant. Now, cars have sensors for the speed. And then there's a reference, is what I want, either the speed that I set or the speed of a car in front of me. And then what are the disturbances? So if I'm following a car, most of the time the disturbance is the road condition. If I don't switch lanes, then the road condition is going to be my disturbance. If I'm going uphill, then it's going to be more challenging if I keep the throttle at the same angle. I need to put more torque to the car. If I'm going downhill, then less torque, right? So the road condition is the disturbance over here. That's an example about what we call regulation control. I have a desired speed, okay? If there's no car in front of me, I want to keep the actual speed of the car exactly the same as the set number. All right. We talked about control objectives. I would like to quickly wrap it up, summarize it, to list some of the control objectives that are very common in practice. So control objective can be either stable, the system is going to be more stable, right? So human control of the temperature in the house is not as good as a good thermostat can do. It's either better stability or performance. Or it can be there are disturbances in the process. So our objective is to be able to make the system output exactly the same as best as we can in presence of these disturbances and noises. Regulation is a very common term in practical control systems. And then it may be also we want to be able to track. The main objective is to track some reference command. It's not to be able to stay at a given number all the time, but there's a profile that the control system wants to track. So tracking control is another class of control objectives. These are pretty common. And then robustness is something a separate class will treat more heavily, robust control theory. The idea is actually pretty important and straightforward. The idea is, in practice, there's lots of uncertainties in the system that we control, right? So I may think that my car moves, I put throttle, and then I get speed outside. So maybe it's acceleration translate to speed, translate to position. So that's like integration, simply. But in practice, it's not really that simple. These things, the model that we built to formulate the plant is not perfect. It can be uncertainties in practice. But what's amazing about control is that it turns out using advanced control techniques, we will be able to control an uncertain system reasonably well so that it can behave in the way that we want. This is very important and really exciting field. Control objective can be just I want the system to be robust. And then sometimes these objectives, they will occur at the same time in practice. So there may be time that I want the system to be able to, I want to ensure stability, and then in the meantime, I want to be able to do regulation or tracking control in presence of uncertainties. Different applications will call for different objectives over here. And how we do to be able to achieve these objectives is as follows. Okay? These are the main things that I want to highlight in this class. The way that we build control systems to do robustness control, tracking, or regulation, they are roughly follow the same pattern. First of all, we need to be able to have a good understanding about the process. We need to be able to understand what we are controlling in order to do well, right? So the first thing we do is to model the plant. These are usually mathematical models that we describe either from ordinary differential equation, transfer function is one class. We need to have some abstracted mathematical description of the system. And then having the model, we can analyze how it looks like. Hopefully, by the end of this quarter, we'll provide you enough materials so that when you look at a formulation, when you look at a plant, when you look at a state space description or a transfer function description, without doing any controls, you can have a better understanding. You can have a good understanding about how it looks like. Is it going to be difficult to control? How fast? What kind of speed can I control the system? All these kind of things. Hopefully, by the end of this quarter, you will have the technology, you will have the insights to be able to tell right after modeling step. And then after you look at the system a little bit, you can design algorithms. You can design controllers. After doing the design, then you can see how it fits, whether it's meeting what you expected. So you analyze again the performance, robustness of the control system. You may iterate a little bit in your design, and then you implement it. Usually, designing the control algorithm is on a computer. You do simulation or you do calculations, and then implementing controller is done on a physical system. I will teach you how to do model, how to design controllers, and then how to implement controllers. But in the meantime, what I hope is that through this computation, you gain insights, not just the numbers. I will analyze as much as I can about these techniques and then build examples to illustrate these concepts. That's a rough, big picture of the terminologies of control systems and what this class is going to cover. You can go, obviously, way beyond what this class can offer. Some of the resources are listed over here. There are many societies of control systems from IEEE, which is more focused on aerospace. There are also ASME, American Society of Mechanical Engineers. They have a division of Dynamic Systems and Control Division that do a lot of applications and research into controls. These societies, they all have their own publications. So IEEE, they have Journal of Guidance, Control, and Navigation. So you can tell pretty much what this journal is going to cover. In ASME, Journal of Dynamic Systems, Measurement and Control, this is a little bit easier to start with. So I encourage you to read some of the materials here before moving to other societies. Then there's also IEEE. This is more electrical engineers, but now it's quite mixed. Mechanical engineer, electrical engineer, aerospace. They all publish in IEEE. They have a control system society, and they have different publications. This is a very good publication to start with, Control System Magazine. It covers both applications, theories, as well as tutorials that are very exciting to read. There are more technical or advanced publications, Transactions on Control Technology, and then Transactions on Automatic Control. Transaction on Automatic Control is math heavy. Transaction on Control Technology is usually brings a little bit more application examples. There's also International Federation of Automatic Control. This is a very big society, and they have publications of Automatica Control Engineering Practice. This is also more math heavy, and then this is more applications. This also contains a lot of applications. You can experience a lot by going to these available resources. Here are just some examples about IEEE Control System Magazine. They have different issues. Some focus on robots on the ground. Some focus on robots that flies. Some may focus on aircrafts, vehicles, etc. That's where you can go beyond what this class will offer. Any questions?